Okay, in this particular question, we're trying to find the value of angle ABC. And this particular question comes from a larger group of puzzles called Langley's Adventitious angles. And so basically we can reduce this to a bit more of a general problem. And we rely on a little bit of a trick to help us get started. If you were using some basic geometry to start, you'll make some progress, but then you'll kind of hit a wall. And without the trick, it's very, very difficult. It is possible, and you can use a lot of trigonometry and sine and cosine rule to get there. But we're going to go with the method of using the trick. And I know in maths, there's obviously a fine line between a trick and a technique. But oftentimes with things like geometry, a little trick can help us save a lot of time. So to begin with, we're going to do a bit of construction. We're going to add in a 20-degree angle to the base DC that intersects the line BC. So we're going to add that in first. So I'll try and make it as accurate as possible. But I should say that my diagram isn't exactly perfect, so it's not to scale. Okay, so let's call this point E. And I'm also going to add in a second line from point E to A. And that is all the construction that we will need. Okay, so we're going to construct a 20-degree base angle, which means that this angle here will have to be 40 degrees. Now you might say, well, how did you come up with that? Well, I didn't. This solution has been around for a while, and it's very, very neat. And oftentimes when solving these geometry problems, it involves a lot of looking beyond what we're given. And you're trying to create relationships often by looking outside of the box. And so that might involve you taking just particular triangles in this case and maybe translating them or reflecting them, moving things around, a lot of outside the box thinking. So yeah, this particular trick is pretty sneaky, but it will help us find angle ABC. Okay, so let's just make a note of that. So we construct line DE, okay, so such that angle EDC, which is the base angle, is equal to 20 degrees. Okay, and then we made that construction from E to A. All right, so the first thing that we can kind of spot is in triangle DEC. Okay, so looking at the bottom triangle, we should all be able to hopefully see that this angle here will be 80 degrees, just using our interior angle sum. As we have a 20 and then an 80 degree here, that's 100, and then 180 take away 100 leaves us with 80. So angle DEC is equal to 80 degrees. So looking at triangle DEC. Now I'm not going to write all my full reasoning just for the sake of time in this proof. So I'll just say to consider triangle DEC. All right, so here we should also notice another relationship, two base angles being equal. So that means that triangle DEC is also isosceles. So 80 degrees in the two bottom angles. So let's mark that in on the diagram and then make a note of it over here. So DE is equal to DC. Okay, triangle DEC, oops, is isosceles. Okay, so now let's move on and we're going to, I think you can see the pattern here is basically we're going to work our way up until we can get to that top right hand corner by using these little relationships that we can find and these smaller triangles contained within the larger quadrilateral. So now we can see that angle ADE is 60 degrees, the 20 and 40. So angle ADE is equal to 60 degrees. Okay, that's just a fact. Now, if we consider the angle DAC, so now I'm looking at triangle ACD, we can again use the interior angle sum to find the angle DAC. So we have 20, 40, 20, and 50. So subtracting that from 180 will leave us with 50 degrees. So we can say that DAC is equal to 50. Okay, so that is by considering the angle sum of triangle DAC. Okay, so I'll just put that there. All right, so again, we should notice that we have two equal base angles, 50 degrees and 50 degrees. So that means triangle DAC must also be isosceles. And I'm going to use the same marking because that means AD is the same as DC, which is also the same as DE from earlier on. So let's make a note of that. So now we have side AD is equal to side DC. So triangle DAC is isosceles. Okay. So now we can conclude that DE is equal to DA as well. So we have three of these lines that are equal. So that means, so let's just write that. DE is also equal to DA. Okay, so that's a consequence of, let's maybe just put some, so let's just put a 1 and a 2 here. So as a consequence of those two steps, saves me writing too much. As a consequence of 1 and 2, we can say that DE is equal to DA. So we have another isosceles triangle. So ADE is also an isosceles triangle. Okay, so now we can say that angle DAE, so bear in mind that this angle here is 60 degrees. Okay, and now we know that triangle DAE is isosceles. So triangle DAE is isosceles. So if the angle that I just marked in red is 60 degrees, that means we have 120 degrees left. And as we know, isosceles means the base angles must be the same. So that means angle DAE and angle AED must both be 60 degrees. So let's make a note of that. So angle DAE is the same, because it's a base angle, as AED. And because we had 120 degrees left and we have to halve it to get each one, they're both going to be 60 degrees. Okay, so this is considering triangle DAE. Okay, so let's add that in. So we have, and hopefully we should see another interesting relationship. So 60, and that whole thing is 60 there. Right, so if three angles are 60 degrees, that must mean that that triangle is equilateral. So that means side AE is also equal to side DE as a consequence. So let's make a note of that. So DE is equal to AE. So DE is equal to AE as triangle AED is equilateral. Okay, so we're not too far off getting our final solution. So now that we've set up that equilateral triangle with all of those angles being 60 degrees. Okay, looking at now the straight of BC, we can conclude that, well, this angle here must be, okay, 100, and so this angle plus 60 plus 80 must be 180. So angle BEA must be 40 degrees. Okay, just looking at the supplementary angles on a straight line. So angle BEA is equal to 40 degrees on a straight. Now, if we consider if we consider triangle DBC, we have 40 degrees and 20, so that's 60. And then we have 50 and 30 in the bottom right-hand corner, and that again leaves us with 40 degrees in the top corner here. Okay, just using interior angle sum again. So I think you can see the pattern again that I'm making another isosceles triangle. So this time, also, angle DBE, I think it was, is equal to 40 degrees, considering the angle sum of triangle DBC. All right, so that means, again, we have an isosceles triangle. So this side here, so E and E to B, okay, we can also mark to be the same as what we have over here. So I'm going to add that line here. So DE is equal to, why does it keep doing that? Okay, so DE is equal to EB. I think it must be the table format. EB, okay, now reason again will be the base angles in triangle DBE. Okay, so we're very close. Sorry, that should have been just for that angle there, just so it's clear. All right, so we're nearly there. So now all we have left to say is that this angle here, angle BAE, so I'm looking over here, this angle here must be 70 degrees. Okay, because now I'm considering triangle ABE. Right, so we've just said that DE is equal to EB. Okay, DE is equal to EB. Okay, so that was that part there. Okay, so that means in triangle ABE, we already have a 40-degree angle here that's taken up. So again, 180 take away 40, it leaves us with 140 degrees. And because this is another isosceles triangle, that means I have to split it in half again. So that means 140 divided by 2 is going to leave me with 70 degrees. So that means both of these angles must be equal to 70 degrees. And I think you can see that we're going to get the answer there. So angle BAE is equal to 70 degrees. Okay, considering triangle ABE, again using our isosceles pattern. And so therefore angle ABC, right? ABC in total must be 40 plus, well, it'll be 30, which is going to be 70 as well. So that gives us angle ABC. Okay, so in conclusion, therefore, angle ABC must also be equal to 70 degrees. And we are done. Okay, so I guess in conclusion, this wasn't an easy problem. And even though I've used fairly basic geometry, using interior angle sum of triangles and isosceles triangle properties and a bit of straight line rules, nothing there that was beyond the scope of stage 4. However, I guess the challenge was the beginning and setting up this relationship between all those little triangles. And it's very, very hard to actually think of that particular strategy to start with. And the other alternative is to kind of brute force your way through using trigonometry, but it is a lot more complex. But I hope you found that interesting and engaging, and I'll release another problem sometime next week. So I hope you enjoyed that, and see you in the next video.